Good afternoon. Today we're going to start on a new topic. The topic is parameter estimation. Okay. There are two things. I'm sure you heard these terms before, the population and the sample. The population is usually something that is not accessible. Like, for example, all men in the UK. I mean, there are millions, so it's impossible to access every single man in the UK, right? The sample is a subset. It's usually a small subset of the population that is accessible. So a sample could be like maybe 100 people or 100 men or 1,000 men. So that's something that can be accessed easily, right? Okay, now right? The notation I shall use in this course, and probably in other courses you have taken in the past, is theta. Theta is the common notation to denote a population parameter, or in other words, a parameter that is associated with the population. Theta hat is an estimate of theta based on a sample, right? So, for example, theta could be the average height of all men in the UK. Obviously, it's impossible to access all the men in the UK, so it's not possible to give an accurate estimate of theta, right? So what we usually do is we draw a subset of all men in the UK. So it could be like 100 men or 1,000 men, right? And for that subset, we measure the height of the height of every man in that subset, and then take the average. So theta hat could be the average right? Theta hat could be the average height of 100 men selected from the population, right, in the UK, right? So that's one example of theta and the theta hat, okay? Now, let me put this over here. Hopefully you can see this. Oh, sorry. Suppose let's denote x1, x2 to x100, the heights of the 100 chosen men, okay? How do we estimate the average? The question, how to estimate the average? Obviously, there's no one way of estimating the average of 100 men. So, for example, you could say that theta hat is equal to this is one possible estimator of theta, okay? But that's not the only possible estimator of theta, right? You could also estimate theta hat as the you could also estimate theta hat as the median. I'm sure you know what a median is, right? You must have done this in you could also take theta hat to be the median of the numbers from x1 to x100, okay? You could also take theta hat to be you could also take that to be that, right? So here you're just summing the first and the last heights and multiplying by 50 and dividing by 100, all right? So there's no one way of estimating the parameter theta, right? The question is, how do you estimate the parameter theta so that the estimate that you get is the best one, right? How do we estimate the parameter so that the estimator that you get is the best possible estimator? Now, to answer that question, I need to define two things. Let me put this here. The first thing sorry. Sorry, guys. How to choose? I mean, there are, as I say, as I explained over here, there is no one possible estimator for the average theta. Now there are three. I mean, these are just three, but there are many more you can write down. Okay, so to answer this question, I'm going to introduce two things. One is called the bias. The bias of theta hat is defined as the expected value of theta hat minus the true parameter theta. Two is called the MSC, stands for mean squared stands for the mean squared error and is defined to be the expected value of this. Okay, so these two formulas, right, tell you how good an estimator theta is, right? So a good estimator a good estimator will have the bias of theta hat equal to 0 and the MSC of theta hat equal to as small as possible, right? So for example, if you return to this example here, right, here I have listed three possible estimators, right? So what you can do, you can compute the bias and the MSC for each of these three estimators and choose the one that has bias equal to 0 and the MSC as small as possible. And that will be the best estimator for theta. Is that clear, guys? Yeah? I mean, these are two criteria. The criteria is the bias and the MSC. So you want to choose a good estimator, and a good estimator will have bias equal to 0 and the MSC as small as possible. Okay? There are examples. I think we will come across some examples later on. We will come across some examples later on where the bias will never be equal to 0. You guys okay? There are examples that we will see later on where the bias will never be equal to 0. Yeah? So in such situations, you want to select the estimator that has bias as small as possible. So in this case, in such cases, right, or cases, choose in such cases, so you cannot eliminate bias, right? In such cases, you need to choose the estimator. You need to choose the estimator for which the absolute value of bias. I'm sure you're familiar with this sign, right? Which means the absolute value of bias is as small as possible, right? Okay. So sorry, guys. Suppose you have two estimators, say theta 1 hat and theta 2 hat of theta, right? In this case, and you want to choose between, I mean, this is a typical question I normally ask in the exam. Like in the final exam you will get in May or June of this year, you get a question like this, that you will always, well, every year I ask a question like this, that I give you two possible estimators for a parameter, and ask you to choose which of the two is better and why. Okay, you will always get a question like this, right? So to answer such questions, this is what you need to do, right? You compute to answer this question, what you need to do is the following. Compute okay, and also compute okay. All right, so you need to compute the two biases and compute the two MSCs. And then say if the absolute value of the bias of theta 1 is less than the absolute value of the bias of theta 2, then you will say that theta 1 hat is a better estimator with respect to bias. Okay? And similarly, if the MSC of theta 1 hat is less than the MSC of theta 2 hat, then you will say that theta 1 hat is better with respect to MSC. Okay? So these are, These are the two things that you need to look for when you answer the question, right? Compare the biases, compare the absolute values of the biases, because remember, the biases can be negative or positive, whereas the MSC, by definition, MSC can only be positive. MSC cannot take negative values by definition, whereas bias can take both positive and negative values. Yeah. Okay. Definitions. The first one, an estimator is said to be unbiased if the bias of it is equal to 0, right? The second one, definition 2 is that an estimator is said to be consistent if the limit of the MSC as n approaches, n is the sample size, approaches infinity, is equal to 0. So that's a good thing. So the two definitions, unbiasedness and consistency, are both properties of a good estimator, right? Number 3, an estimator is said to be asymptotically unbiased if the limit of the bias as n approaches infinity is equal to 0, right? Okay. So these are the three. These are the three definitions I need to tell you. Other thing is properties, okay? Property 1 is the following. You might have seen this. Had you seen this property before in your previous courses? Yes? No? You haven't? This is an important property which says that the MSC of an estimator can be written as the sum of the variance and the square of the bias. Now, I'm going to show you how to prove this in a minute. So, let me pull the chair. To prove this property, you can either start from the left-hand side or the right-hand side. In this case, I prefer starting from the left-hand side because that's shorter, right? Okay? But you can start from either direction. Right, so let me start with the left-hand side, which is the MSC of theta hat, right, which okay, this is the definition of MSC I gave a few minutes ago. I'm going to write this do you see what I've done here? What have I done? I have written theta hat minus theta, but I have introduced two terms, the minus of the expectation of theta hat and the plus of the expectation of theta hat. So I haven't changed anything. Okay? Now, I'm gonna put brackets around bracket around the first two terms and a bracket around the second two terms. Right? Now, if you do the expansion, in other words, open the brackets, you get three terms. The first term is this is the first term. The second term is this, and the third term is is that clear, guys? Can you see what I've done, guys? I'll just open the bracket, right? And you open a plus b squared, you get a squared plus b squared plus 2ab. So you get these three terms, right? Now, the expectation is outside the bracket, outside the square brackets. So I'm going to take the expectation inside. So you get three expectations. The first one this is the first expectation. The second is the second expectation, and the third expectation is it's this one. Yeah. So I've taken the expectation inside the brackets, the square brackets, so giving you three different expectations. Yeah. Now, let me ask you, what can you say about this, the first expectation? What is that? The first expectation, that is this term here, is equal to, do you guys remember what is called the variance? I'm sure you do. the first expectation is equal to the variance of theta hat. Yes? That's the definition, right? Now the second expectation, if you guys look at this term is a constant. I mean, the term that you have here is a constant. In other words, it's not a random variable. Now, the expectation of a constant, you should remember, is itself, right? So, when you take the expectation, what you get is simply that. Yes? Now, over here, the third term, the third expectation, once again, this guy here, this term here is also a constant, right? Now, the expectation is outside, right? So what you have is the expected value of a random variable multiplied by a constant. So what can you do? You can pull the constant, you can pull this constant outside the expectation. So it becomes are you guys with me or no? You see what I've done? This being a constant, you can pull it outside the expectation side. And that's precisely what I have done here, guys. I have pulled this constant term outside the expectation to get this, okay? Right, now next line, the variance of theta hat. Now this thing, you should remember, just a few slides ago, I defined the bias of theta hat as the expectation of theta hat minus theta. So what you have here is simply the bias of theta hat powered to 2, right? Now, let's deal with this term here. You have this. Now, listen guys, I'm going to take the expectation here inside the square brackets. So you get the expectation of theta hat minus the expectation of theta hat. Are you guys with me? Now, what's the expectation of theta hat? Yes? Remember, the expectation of theta hat is a fixed number, it's a constant. So the expectation of that is also the same constant. So this is, yes? Well, because what you're doing here, guys, is you're taking the expectation of a constant. So it's itself. So you have expectation of theta hat minus the expectation of theta hat. So this is equal to 0, right? So what you have is the variance of theta hat squared, which is the right. Is that clear, guys, or not? I mean, it looks like a long proof, but it's not. I mean, is that clear, guys? Or yes? Yeah? Okay, good. Yeah. I mean, some of you might have seen this before. Sorry. Okay. Next, that's one property This is property number 2, which says that if the expectation of theta hat is equal to k times theta, where k is a constant, then theta hat divided by k is an unbiased estimator for theta. Now, how do you, this is really easy to prove. The proof of this, to show that something is unbiased, you need to show that the bias of this is equal to 0, right? Oh, sorry guys, sorry. All right, so we have proved that the bias of theta hat divided by k is equal to 0, and therefore theta hat divided by k is an unbiased estimator for theta. Okay? Is that clear, guys, or no? Any questions on this, guys? No? This is property 3, which says that if theta hat is a consistent estimator for theta, then the variance and the bias of theta hat approach 0. Oh, sorry. I'm sorry. The variance and the bias of theta hat approach 0 as n approaches infinity. Right? Now, this is very easy to prove. Right, since theta hat is, remember the definition of consistency says that the limit of the MSC as n approaches infinity is 0, right? So this implies And this implies, because both these are positive terms, the variances can never be negative. And the square of any number can never be negative. So what you have is the sum of two positive terms, right? So the only way that the limit can be 0 is if each of them is 0, right? So this is true if and only if the limit zero and all right, guys. So that proves property 3. Okay. Is that clear? Yeah. Now, so here we go. This is property 4. It's really an easy property. It says that if theta hat is an unbiased estimator for theta, then the MSC of theta hat is equal to the variance of theta hat. It's really easy to prove. Right, this is really trivial because by property 1 we have this result, and theta hat unbiased means that the bias is equal to 0. That means this term is 0, and therefore the MSC is equal to the variance. Okay? Yeah. So these are 4 properties. Now I'm going to do some examples if I have time. Now this is why you need to use your examples booklet. You guys have copies of this? Yeah. If anybody hasn't got a copy of the lecture notes or this one, please could you see me out in a couple of minutes? All right. All right, can we look at, listen guys please. Can we look at example 9? Hope you can read it. So you have basically x1, x2 to xn. Right? where sigma squared is known, and consider the estimator x bar is an estimator for mu. Find its bias, MSC, variance, and check whether it is consistent, right? All right, to find the bias, remember the definition I gave you. The bias, remember, the bias is always the expectation of the estimator minus the population parameter that you're trying to estimate, okay? So this is 1 over n times the expectation of the sum of the expectation of xi minus mu. So this is 1 over n times. Now what's the expectation of xi if xi is normal? Yes, you should remember this from last week, guys. It's equal to mu, right? Minus mu. So this is 1 over n times mu minus mu, which is 0. So the bias, so the bias is equal to 0, right? Yes? So the next thing we need to find is the MSC. Now, I just proved just a minute ago that if the estimator is unbiased, then the MSC is the same as the variance. So what you need to find is the variance of x bar. So let's do that now. The variance of x bar is the variance of this. Now when you take the variance inside, guys, you remember when you pull a constant outside the variance, you need to square it. You remember that, yeah, from previous courses. Yeah, so this becomes, yeah, so this is 1 over n squared times the sum, the variance of xi for a normal distribution is sigma squared. So this is 1 over n squared times n times sigma squared, which is sigma squared by n. And this approaches 0 as n approaches infinity. So therefore, what you have is that x bar is unbiased and consistent for mu. All right, guys. So we computed the bias, we computed the MSC, and we have proved that the estimator is unbiased and consistent. All right, guys. I'll see you tomorrow or next week. If you have any questions, feel free to come and see me in my office. I mean, you are welcome to see me anytime. No appointments needed, right? And if you don't have copies of the lecture notes, could you please come forward? Thank you. that's okay.
May I ask you something?
Yeah, sure.
Let's say you have two estimators of theta,
Yeah.
and can the, let's say, bias of theta 1 be less than bias of theta 2? But
Yeah.
the MSE of theta 1 be greater than...
Yeah, you can have situation. That's why I said you need to write with respect to bias, this one is better, and with respect to MSC, this one is better.
Okay, so maybe we have that theta 1 is better with respect to bias and theta 2 is better with respect to MSC.
So that's the final answer. We say that.
Yeah. See you, man. Hi. Yeah.